Okay, we are recording. All right, in terms of rest of the semester, I told you there was going to be one more project, and that is true. It's probably going to be perceived as a horrible project, but really there should not be that much new code that you need to write. It's going to be reusing a lot of the stuff that you have or should have already written previously. So I've got to finish doing the analog read potentiometers today. Then we're going to start what is basically an analog write, where you can vary the brightness of the LEDs, or you could use this to control the speed of a motor, for instance, or any kind of a device that you can pulse. And then at the end, I'll talk a little bit about the project, the write-ups. I'll show you what I've got written up so far. It's not quite perfect yet, but it's close. So let us share the screen here. Let's see, that I can minimize. And that's on my screen. Share screen, screen 2, that's interesting. Okay. All right, and hopefully you see the program we were working on last time?
Yes.
Okay. All right, last time, just to review, we had done this code looking at how the analog to digital converter works. And we wrote a routine. We had looked at all of these flags in each of these registers for the ADC. We are using the ADC in polling mode, not interrupt mode. So basically we ask the ADC, we call this routine. This line says, okay, start a conversion. When I set that AD start conversion bit to 1, that starts a conversion. When the conversion is done, this ADIF is set to 1. So I spin as long as that's 0. When it's finally set to 1, I return whatever's in the ADC register, 16-bit version of the high and the low. And I tested this out by writing some code here. And all I do is output that result to port D, which doesn't do a whole heck of a lot. But if I plug, here's the end of my cord. I plug my board in here. And the channels that are useful here are channel 0 is the leftmost pot, channel 1 is the middle, and channel 2 is the rightmost pot. So just to do what we did last time, the pot's all the way counterclockwise now. I've got a breakpoint set at this line. I need to make sure that it sees this particular board. Is that the right number? I can't tell, it's worn away, we'll find out. Let's start debugging and break. Okay, we're at the beginning now. I'm going to hit F5 to continue. And it stops at this line about to be executed. Let's hover over result. The result is 0. The pot is all the way to the left. Let's turn the pot all the way to the right. And F5 this again. We're now at the breakpoint and result is still 0, which I didn't expect. Let's try, do I have these pots backwards? Okay, sorry, but. Oh yeah, okay, if you look at how the pots are labeled on the board, P1, even though I know it's channel 0, it's labeled P1, is all the way to the right. So channel 0 is the one all the way to the right, my mistake. Now it's 1023. You see it here? If I set the, if you can see that, if I set this pot somewhere in the middle, Guess that's about the middle there. And I F5 this again. 661 in the middle, exactly in the middle would be 512. So I'm in the right ballpark. All the way to the left should be 0. F5. Okay, it's 0. Turn it up just a fraction. F5, 59. So that's looks pretty good to me. If I were to change this, let's say stop debugging, just to make sure, let's change this to a 2 and run this again. Start debugging and break. At the moment, let's see the leftmost pot. Oh, let's turn the leftmost pot all the way up. And I hit F5, 1023. If I turn it about halfway down, in F5, it's 314. I guess I turned it a little more than halfway down, but I turn it almost all the way down. 13, all the way down, 0. Okay, and just for good measure, let's check pot number 1. Stop debugging, start debugging and break. All right, pot 2 is all the way down at the moment. F5, 0. Turn it about halfway up. F5, 565. Middle pot all the way up. 1023. Let's twiddle the left and the right ones. Should still be at 1023. Still at 1023. So that looks pretty good. Right, so I have a way I can write a 10-bit value. I can read a 10-bit value. I read it in a 16-bit register. But the upper 6 bits are always going to be 0. Now, there might be a time when you don't need 10 bits worth of precision. You might only need 8 bits worth of precision. Now, that means each turn of the pot, or whatever the reading is going to be a bigger increment. I think it's 20 millivolts instead of 5 millivolts. On the other hand, if that's good enough, then there's no reason to deal with 10 bits. If I was dealing with a temperature sensor, I'd probably want very fine resolution. If I was dealing with the brightness of an LED, probably 256 different possibilities is good enough. Even with some high-end graphics cards, you've got 8 bits for red, 8 bits for green, 8 bits for blue, which gives you better than 16 million colors. If you have really high-end graphics cards, they typically do, I guess it's 10, 10, and 12 bits for, I think, the green, because your eye apparently can discern green a little better than red and blue. That's really high-end graphics cards and gets you 32 bits total. But in general, 8 bits for a color is pretty good. All right, so let's look at this analog read 16, and I can make this into a 8-bit routine pretty easily. I'm gonna copy and paste this. So there's my 16-bit routine, and Control-C and Control-V. And the only difference I'm gonna do here is I'm gonna change this into a uint 8 as a return type. The name is going to be analog read 8. And the one difference is this left adjust result. I am going to change that to a 1. The result of the A to D is always going to be put into, basically call it a 16-bit register. It's a high and a low, but let's call it a 16-bit register. If this left adjust result is a 0, it's not left adjusted, it's right adjusted. And you get a 10-bit value. 8 bits are in the 8 bits of the result are in the lower 8 bits. The high 2 bits of the result are in the upper byte. If I make this bit a 1, the whole result is left shifted. That means the most significant 8 bits, the result is still 10 bits, but the most significant 8 bits are in the high byte. The least significant 2 bits are in the highest 2 bits of the low byte of the result. Now here we just grab the whole result. Here I'm going to say ADC H, just return the high byte. Change the comment there a bit. Right now, if I use analog read 8, I should get a value between 0 and 255, 255 when it's full, 0 when it's all the way to the left. So let's come along here, change this to analog read 8. That's still the center potentiometer. Stop debugging. Start debugging and break. I'm going to do my best to set this potentiometer about in the middle, which I think is about there. So I just set the center potentiometer to the middle. I'm going to say F5 to run this. And hey, I did a really good job. 127, 128 would be dead center. If I do this all the way to the right and F5 it, I should get 255. Get 255. Let's do all the way to the left, not quite. Okay, 12, all the way to the left, 0. Okay, so what I have here very nicely is a routine that will give me 8 bits of an A to D reading, and I've got a routine that will give me 16 bits. Both of those are going to be useful in your last lab. I guess really more the 8 bits is going to be useful in your last lab. But any questions on that? All right, then let's save that. Let's close that actually. Save it, close it, and after class, I will get on the VPN and move that into the onto the M drive. All right. Next piece, actually, let's all right. All right, let me talk about what's going on here. Pieces for the last lab. You are going to be using the serial port. You are going to be typing commands to your board. Commands are going to be something along the lines, actually these, okay, let's look at please. For the most part, it's single digit commands, possibly, or in some cases with a argument. If I type a 1, a 2, or a 3, that's going to put this board into what I'm calling 7-segment mode. And if I type a command of 1 in PuTTY, that's going to set the board so the leftmost pot displays a value 0 to 1023. If I type a 2, the display is going to display the value of the center pot, and a 3, it displays the value of the right pot. If I type an R, a G, or a B, it is going to put the board into LED mode, and the pots are going to control the LED, the brightness of the LED, the red, the middle pot, the green, the right pot, the blue. I haven't showed you yet how to adjust the brightness of the LED, but that's what we're going to start after I talk about this briefly. Now, to make life really interesting, there's also some multi-character commands. An S, a space, and a 1. Each of the S commands will be exactly 3 characters. That is a scale. So after the user types S space 1 and presses enter, you're going to need to prompt the user for a min, and you're going to need to prompt the user for a max. You can assume that the user will enter something between 0 and 9999. You can assume the min will be less than the max. You don't have to value check it. The difference is then you're going to display the setting of potentiometer 1 on the 7-segment display. But when it's fully counterclockwise or all the way down, you're going to display whatever value was entered for min. When it's fully clockwise, you're going to display whatever max was entered. And this should be a linear graduation, so you're going to do a little bit of division. You can do division, it's somewhat slow, but you can do division on the 328. For 2, it's the same, except it's the center pot. For 3, it is the rightmost pot. And just in the interest of giving you a reset command, if you type T, it will reset the board to the initial state, the same as typing R or G or B. So the pieces of this that you have or should have are typing to and from putty. So you should have some UART routines, hopefully, or if you don't have them done, they're hopefully in the process of being finished. You have routines to display on the 7-segment displays, interrupt driven, hopefully. And the thing you don't have is a way to set the brightness of the LEDs. And that's what we're going to look at right now. So this I will hopefully finish up this afternoon. I'll put it on the, I will put it on the website, not the website, on the M drive. And that will be your last lab. All right. Now, at the beginning of the semester, when we first did the LED lab, I heard people say, gee, why didn't you just put this LED on like port B, pin 0, pin 1, pin 2? And I said at the time there would be a reason. This is the pinout of the 328. Red is on what bit? And is that familiar to anybody? The red LED is on what bit?
D6.
D6. Let's look at D6 right here, D6. Note that among the functions that D6 shares, besides just a general purpose IO pin, is OC0A. Okay, keep that in mind. What bit is green on? Anybody? Just want to see if people are there.
I think
Is it D5?
Well, what port is it on? Let's talk about what port.
it'd be on port D.
Oh, it's port B, isn't it?
You know, it's definitely port B, and it's bit 1. So if I look at B1, wherever B1 happens, okay, there. Note that D6 is OC0A, B1 is OC1A, output compare 1A, and the blue is on B3, which is incidentally OC2A. Oh, that is not coincidence. All right, if we go down to our timers, let's look at timer 0. And let's see. Look at our register descriptions here. Okay. If I look at bits 6 and 7 here, timer 0 controls the behavior of OC0A. If I put this in PWM mode, I can control what the waveform on OC0A is just by setting up a few bits, and then the hardware takes care of all the magic. We still have that. Did I close this or do I have it? I do have it up. I think this was talked about a little bit. Just the pulse width modulation thing. Okay, this is from an old lab, but okay, if we talk about pulse width modulation and I have a 50% duty cycle, the high and the low of some square wave is about the same. 75% duty cycle, it's high 75% of the time, low 25% of the time, 25% duty cycle, high 25% of the time, low 75% of the time. Now what the frequency is doesn't make any difference to the duty cycle. So the frequency is one thing I need to set, and then the duty cycle is something else that I need to set. And I need a cough drop, hold on. So these days you have to be real careful about coughing even if you've got allergies. So I normally cough every spring.
Same here.
Yep, okay. Has anybody seen the video of the woman at the bus stop that sneezes? There's a video on YouTube and hopefully a spoof, but a woman sneezes at a bus stop. Somebody immediately pulls out a gun and shoots her, and then everybody sprays everybody else with disinfectant. I don't know if we're going to get to that or not. But different duty cycles. The thing to keep in mind when you are dealing with LEDs in duty cycles, or the LEDs on this board, is the LED is on when it's low. So a 25% duty cycle on the LED is going to be 3/4 brightness. A 75% duty cycle is going to be 1/4 brightness because it's only low 1/4 of the time. So there's kind of a backwards thing there you need to remember. And if you don't remember it, hopefully when you see it, you will remember that. Okay, so by setting this bit to a 1-0, it is going to clear 1-0, right, come 0A. It is going to clear on a compare match. That means, again, we've got to remember back to timers, there was an OCR-A register, and as my T count register counted up, when it reached the value I put in OC, output compare register A, when it reached that value, I could control what the OC0A pin did. And that is what we're going to be doing here. Okay, we're going to look at PWM mode here. Okay, I was a little bit bothered by what I was just saying, but now this makes sense, because if we're in PWM mode, a setting of 1-0, it clears it on compare match and sets it at bottom. We need to look at what bottom is going to be. The table here someplace. Okay. We are, just a second here. In mode 3. Okay, we're going to be in mode 3, which is fast PWM mode. This is probably the most useful, not true? Yeah, most useful mode that there is. The T count register is going to basically count from 0 to 255. It's an 8-bit timer. It's going to count from 0 to 255. At bottom, or 0, the OC0A line is going to be cleared. Let me just make sure that that's right. Is going to be cleared. When it gets to 0, it is going to be set. So T count is going to count 0 to 255, 0 to 255, 0 to 255. At 0, when the T count is 0, the OC0A bit, which comes out to the outside of the chip, is going to be cleared. I'm sorry, going to be set. Going to be set. When T count matches OCRA, it is going to be cleared. Let's see if we can put that into practice in a program. Let's start a new project. Oops. New project. I'm going to call this analog write. All right. Let's just say I want to play with the red LED. All right, I want to play with the red LED. I've got to set the DDR deregister bit 6 to say it's an output. I then need to set up the timer control register A and timer control register B. So TCCR0A needs to equal something. All right, let's go back and look at the data sheet at register A. The 0B output I'm not going to use. The 0A register I need to set. I'm in pulse width modulation mode. 1, 0. I'm going to clear it on a compare match and set it at 0. So those bits I want to make 1, 0. Go back here. COM0A0. Let's go back to the data sheet.
Are you supposed to do that to register A, not B?
AJ, you were breaking up. Say again, please.
Oh, isn't that supposed to work on register A, not register B?
Oh, yeah. Yep. Yep, you are absolutely right. Thank you. Typed it in the wrong place.
Right, thought so.
Yep, thank you. That's good. Let's go back to, okay, COM B, we're going to leave at 0. Wave generation mode. I am going to come down here to the WGN table. I'm going to do fast PWM. Again, probably the most useful mode of the timers. 0, 1, 1 is what I want to put in for wave generation mode. The 2 least significant bits go here. So the 2 least significant bits are 0B11, WGM00. That takes care of register A. Let's look at register B. All right. The force output compare, I'm not going to be doing any of that. This wave generation mode, I need to make 0, since the mode was going to be 3 or 0, 1, 1. Clock scaler. I'm going to do a divide by 64, which is going to give me a frequency of, did I write that down in my notes? I didn't write that down. So what is, let me get my calculator out here.
250,000.
Okay, 250,000, but since I'm generating a wave counting from 0 to 255, or 255, I've got to divide that 250,000 by 256 to get the actual frequency.
And 976.56.
Okay, hold on that number for just a minute, because each tick of the T count register is 250K. But if I look at this duty cycle, it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 128. If I have that if I have the output compare register A set to 128, when T count matches that, it's going to go to 0, and then it's going to be 129, 130, 131, 255. So there's going to be 256 different states. And when you divide that by 256, what is it you get, AJ?
976.56.
176 or 1,000?
976.
Okay, 976, okay. By trial and error, and actually I think I looked at the Arduino library to see how they wrote the code. A frequency of about 1 kilohertz works really well for LEDs. If you were dealing with a motor or something like that, you can vary the speed by pulsing it, same as you can vary the brightness of an LED. You might want to use a lower frequency on a motor since it doesn't react as fast. But sometimes that's a trial and error thing. About 1 kilohertz works really well. All right, so let's go back to the documentation. These 2 bits are going to be 0. That bit's going to be 0. And I'm going to make this divide by 64, which is 0, 1, 1. Okay, so I go back to this, and 0B0, WGM02, 0B011, CS00. Okay. Now, okay. To set the brightness to a particular thing, I'm simply going to say here, OCR 0A equals 128. Let us run this, and my expectation is I'm going to get that LED at roughly half brightness. So start debugging. Now let's just start without debugging. And let's set up this. And why do we get nothing at all? Grid. VDRD.
Where does the 128 come from again?
The 128 is halfway between 0 and 255. So it should be a 50% duty cycle.
Okay.
So we debugging and break. All right, I guess in the interest of debugging, I'm going to go over to my timer. And look at the bits. So again, in interest of debugging, you can go to your IO, click on timer 0, and say 10, 0, 11. That makes sense. That makes sense. Here is 0 right now. I set that to 128. Oh, and then that optimized, okay, it optimized away. Debug, stop debugging. Just put that in there. Zero and 1. Let's see.
Is there supposed to be a light or no?
Yeah, there should be a half bright light. I mean, I'm looking at code on my other screen, which I know works.
Do you have to set the mask?
No, because I don't want to do anything on the, I don't want to have any interrupts on the, on any event. So there's no interrupts I need to generate on an event because the hardware should just do all of this.
When we were doing the LED lab, there was a common anode in port C that we set up.
Yes, thank you, thank you, thank you. That's exactly what it is. And I do that. Yep, thank you. That's exactly what it is. Okay. Yeah, DDRC
63rd bit.
to 1 or 3. Okay. Yeah,
Oh,
that's exactly what it, thank you. All right, so now let's try this. No, debugging. Let's go for the gold. DDRC, oh, okay, and port C. Ah, okay. Now, that should be at, yeah, that looks awful white to me. Okay, and it does look white, and
I think you have to turn off the other lights.
because I didn't never turned off the other ones. They're just floating. And so they're, so let's specifically say DDRB or equals 0B1010. And let's say port B or equals 0B1010. Okay, debug, start without debugging. Okay, with any luck, that looks like a red LED at half brightness. Let's change this to 1. Right. Is that going to be full brightness or is that going to be
Extremely dim.
full brightness or practically off?
Practically off.
Practically off. All right, well, let's see. Start without debugging. Okay, full brightness, because if you are at 0, which a 1% duty cycle, most of the time you're at 0, it should be full brightness. If I do a 254 and I run it,
It's going to be extremely dim.
extremely dim. Okay, I don't know, yeah, you see it, so it is very, very dim.
Yeah, barely can see it.
Okay, you can barely, yeah, you can barely see it. And these LEDs are so bright anyway, that's pretty dim. Let's look at what happens in 255. Running. Okay, 255,
It's off.
pretty much off, because you'd expect it's going to, I guess, really be on for less than 16, over 16 million, something like that, or 64 times 1/16 millionth, on for a very short time. And if I make this 0, I run it. Okay, that's full brightness. So 0 is 0% duty cycle, which means the pin is 0 all the time, and full brightness. Okay. All right, so that's how I would control the red LED. Let's look at timer 1, which OC1A is tied to the green LED directly. So let's look at timer 1. Now, timer 1 is a 16-bit timer. But if we look at register descriptions, okay, control register A for timer 1 looks exactly the same as for timer 0, except instead of COM0A, it's COM1A. I can set that to 10. Look at fast PWM mode. Clear on a compare match, set on bottom. So that's going to be identical. In terms of wave generation mode, we've got 4 bits to control wave generation mode on this particular 16-bit, actually in all the 16-bit timers. So the question is, what mode do we want to put it in? Okay, well, let's look at the possibilities here. Okay, normal mode, PWM, 8 bits. PWM 9-bit, 10-bit, fast PWM. Okay. Which of these modes looks the most like, what do I want to say? Okay, looks the most like the one we were doing. Okay, in fact, fast PWM, 8 data bits, mode 5, is going to basically behave exactly the same as timer 0 did. So for the green LED, things are pretty much going to be the same, except it's mode 5 that you're going to want to set. Wave generation mode 5. Make a note of that. I'm not going to actually write that code, but make a note of that. What about the clock scaler? Let's come to register B here. We're out of time already. Okay. Register B. Again, these 2 bits, we're going to just ignore those for the moment. We're not going to use those at all. The upper 2 bits of wave generation mode are going to be 0 and 1. Lower 2 bits will be 0, 1 as well. Clock scaler, going to go to a clock scaler table, right? It is.
What would the lower bits be again?
Okay, well, the, without answering that question directly, I will tell you it's mode 5. So the whole wave generation mode is 0, 1, 0, 1.
Okay.
2 bits are going to go in register B. These 2 bits go into register A.
Okay, thank you.
4 of the bits together, but they split it up into 2 different registers. Right. If we look at the clock scaler, we want to do a divide by 64, so we get about a 1 kilohertz. 0, 1, 1 will do just fine. And I think that's everything you need to know about timer 1. If we look at timer 2, okay, timer 1, 3, and 4 are together because they're all 16-bit timers. And then somewhere down here, it talks about timer 2. The thing to note about the registers in timer 2, wave generation mode is going to be very similar, but let's look at clock scaler. We're going right to register B. Okay, here's my clock scaler table. Okay, what's different about timer 2? So let me go back to the program for just a second. Okay, clock scaler mode here was 0, 1, 1, which gave us a divide by 64. So 0, 1, 1, divide by 64. 0, 1, 1 here is a divide by 32. Why they implemented it that way, I do not know. But to get the roughly 1 kilohertz frequency, you need to do 1, 0, 0. So that's a change you've got to make for the blue LED. All right, questions? All right.
None right now.
Okay, I will immediately move out the programs that I wrote, and sometime this afternoon, I will have the final lab 8 out, I guess.
So this is the only lab that we have left for the semester, right?
That is correct. Right. What I need to tell you about lab 8, and it pains me to say this, but because of ABET accreditation and stuff like that, on lab 8, the prettiness of your lab report is more important than making it work. It is certainly worth it to your grade to make it work, but to accreditation, the lab should be written more, should put more time into writing the lab on lab 8. Because this lab is going to get submitted to a departmental review committee, and they're going to look at how well you wrote the lab, which ultimately, I don't know, 4 or 5 years from now folds into our ABET accreditation. And you guys may say, well, I'm not going to be here, who cares? Well, there is a big difference in starting salary graduating from an accredited university versus a non-accredited university, unless you happen to be MIT. MIT is not accredited, but they're in a league all their own. But most all universities are accredited, and there's a national review committee that looks at universities about once every 6 years. And this is part of the process to get that accreditation. So my philosophy is—
So, you know, no pressure.
well, and again, it's not gonna, it's more important, not I would say more important, it's equally important to have a good lab report as to have the project work. And generally, in my mind, it was more important to have something that worked than a pretty lab report. Okay, any questions? Good, I will see you on Friday.
Wait, Professor, I have a question.
Sure.
We have, do you have a final or an exam?
No.
I don't think we do.
Nope. What I said was, if I could certainly give you an exam, I don't think it's going to give me much more information. Because of the circumstances of this semester, you can probably get away with a lot and you can probably get a reasonable grade and not learn that much. You at the end of this semester need to really think about how much do I know, because where I leave off, 388 picks up and runs with it. So if you are marginal in this course, you may want to consider retaking it. But in terms of a final exam or another test, nope, there's not going to be another test.
Are the labs going to be worth more for our grade?
This last lab will be worth more. That was one of the things I haven't put in the lab handout yet, but that I'm thinking about, and I will let you know that. So yes, it is worth more because it really integrates almost everything you've been doing this semester. It forces you to integrate it, which is yeah, cumulative type of a thing. And there's a word which I put in the lab report. So system integration is what it's called. And system integration is a big thing. You can make just this piece work, and frequently a design project, in December, the seniors say, okay, I can make this display works over here, and this sensor works over here, and this sensor works over here, and this works over here. Oh, we're in pretty good shape. And then come early February, they put them all together and find out that nothing works. And they find out they're not in good shape. And that system integration is a big piece. So this is your first step or first foray into system integration. Taking a bunch of pieces that you know work, or hopefully you know work, and making them all work together. Okay, any other questions? Okay, I am off to my next meeting. Peace.
Have a good one, Professor.
Okay, you too. Stay safe.
Thank you. Thank you.
You too, Professor.